Hello, Kelly.
Hi.
Hello, hello.
Hello. Hello.
I can't hear you for some reason. Wait, hold on. Wait, is it my computer? Hmm.
Hey, how's it going? I'm
Oh wait, yeah. So, okay. I can't hear you for some reason. What the heck? Wait, can you hear me? Um. Hmm. It's weird. Wait, are you on your phone or computer or laptop? Laptop? Hmm. Yeah, I can't hear you for some reason. It's weird.
Hello.
Oh, hello, hello. I can hear you now. I can hear you now.
Oh, okay.
What happened?
I don't know.
What the heck? You
Like,
trolled me.
the little green thing was moving, and I was like, I'm talking.
Oh my
I don't know
god.
what's wrong.
I saw the green thing too. I saw the green thing on your thing too. I was like, are you trolling me or is it actually me? Because I went to YouTube and I played something and I heard something. I was like, oh, it's not me then. And I was like, huh?
I heard the YouTube thing too.
Oh, but you heard the YouTube thing too?
Yeah, like on your side.
Wait,
I think
what?
I think your mic picked it up.
Oh, what the heck? Thing.
I don't know.
It's crazy. It's crazy. How are you doing for 118A so far?
Sadly.
Sad? Oh my god. Do you have your quiz this week?
Yeah,
What day?
Thursday.
Thursday? What is it on? Like synthesis, alcohol,
Synthesis and alcohol and all of the above.
and all of the above. Oh my goodness. Do you got any practice problems you wanted to try out or anything you wanted to go over? Oh wait, you're cutting out. What
I
was that,
just don't
Kelly?
understand anything.
You just don't understand anything? Oh my gosh. Um,
You
hmm.
froze.
Oh, I froze.
Yeah.
What about now? Is it better now?
I can hear you now. You're moving now.
Okay, that's good.
But I didn't hear anything you said after
Hmm.
I talked like 7 seconds ago.
Yeah, I see. Um, hmm. Do you have a practice quiz or practice like thing that you have from Canvas?
I just have practice quizzes from practice exams from Levens and Way.
Yeah, could you send that to me through email?
Yeah.
Thank you. Hey Wiley, how is 128B going so far this quarter?
I learned so much today. I don't even know what's going on.
You saying so much today? The
Like,
last thing you told me you learned was ester hydrolysis, right? Like in
yeah,
acidic and
no,
basic
we moved on
conditions.
to saponification and then
Saponification.
uh amide hydrolyzation or hydrolysis,
Mm-hmm.
hydrolysis,
Mm-hmm.
substitution using um alcohols and then anhydrides and then transesterification and
Oh
then
yeah.
substitution with ammonia.
Yeah. There's a lot. There's a lot, especially for this
We covered
carboxylic
so
acid
much.
derivative stuff. Like
Yeah.
8B is currently on this stuff right now.
Oh, really?
Yeah. Uh-huh. No, it's a lot of stuff for sure. But the main thing is the nucleophilic acyl substitution reaction. Like that's the main mechanism for
Yeah.
all of those reactions, you know, in acidic conditions versus basic conditions. So, let me show you the general mechanism for nucleophilic acyl substitution.
Did you
And then
ever
I
watch
want to go
Shenanigans?
over the reactivity of the different derivatives that you learned about, like the acyl halide, the anhydride, the carboxylic acid, the ester, and amide, right? And
Okay.
then which ones require what? And then after that, like, it will like give you a bigger picture of what's going on behind all those reactions, you know?
Yeah.
So, the general mechanism for nucleophilic acyl substitution is going to be in either acidic conditions or basic conditions, right? But let me show you the general reaction first. You're going to have an acyl group or carbonyl group attached to some leaving group, Lg, right?
Yeah.
And let's say we are in acidic conditions here. We're going to react that with H2SO4, strong acid. That's the most common
Mhm.
acid that we use for acidic conditions, and some kind of nucleophile. And that nucleophile is often associated with a proton that is going to get eventually deprotonated in the mechanism, right? Because in the final product here, we see that we're going to substitute the leaving group with the nucleophile,
Yeah.
right? That's in acidic conditions. You could have done that in basic conditions as well, right? Where you have a negatively charged nucleophile and the nucleophile solvent that's neutral, like that, which would also, you know, substitute the leaving group with the nucleophile that you have on the reagent, right? So the first reaction here is in acidic conditions. The second reaction here is in basic conditions. But there's two carboxylic acid derivatives that do not require acid and or base condition, right? They can work in neutral conditions, and they're the top two most reactive derivatives, right? Can you tell me which ones they are? Like the most.
Well, I don't think we covered them all yet.
Oh,
We're
okay,
still on
okay, okay.
next lecture, but
Mm-hmm.
we covered like we just started.
Right, right, right. Um, the most reactive derivatives would be the acyl halides, right? Where X could be chlorine or bromine, or the anhydrides, the one that you just went over, right? Which is gonna be something like this, where the leaving group
Oh,
for the
I
acyl
think I have
halide.
like a um least stable to most stable.
Mm-hmm.
It's acid. I wrote acid chloride is
Mm-hmm.
less stable than anhydride, which is less stable than esters. Um, which is yeah, and then
Mm-hmm.
that's less stable than amides, and then the carboxylate the most stable.
Mm. Carboxylic acid. Oh,
He,
did you?
he just wrote carboxylate.
Oh, carboxylate. Yes, 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 yes. So acyl halide is the least stable, anhydride is like the second least stable, and then I'm gonna put carboxylic acid, a neutral carboxylic acid, right here,
Uh-huh.
and then an ester right afterwards, and then an amide after the ester. But keep in mind that this amide here could be like, it doesn't have to be NH2. It could be like NRH, or it could be NR2,
Yeah. Okay.
right? And then carboxylate is the most stable, right? So, like we just talked about, going in the direction of like the purple, right, left to right, is gonna be in terms of stability,
Uh-huh.
right? Um, and we know that in OChem, stability and reactivity are inversely related. So reactivity is gonna increase from right to left,
Mhm.
right? That means that the acyl halide here is the most reactive derivative. Carboxylate is the least reactive derivative. And there's two factors that describe the reactivity of these derivatives, right? I'm gonna draw those two factors out in pink. The first factor is gonna be about leaving group ability.
Okay.
And I'm gonna circle out all the leaving groups of all of these derivatives in pink like that. So all of these pink circles here are the leaving group
Mhm.
of the acyl chloride. Not acyl, of the acyl group. So I'm just gonna draw out the leaving group leaving, because when the leaving group leaves, it will leave with -1 charge, right? All of these groups here are neutral, so when it leaves with a negative charge, except the carboxylate, right? The carboxylate, when it leaves, it will leave it with a -2 charge if it can, right?
Yeah.
This X minus here is the best leaving group because it can handle the negative charge the best. It's the most electronegative atom.
Yeah.
Right. Why is this leaving group here, like the negative charge on the oxygen, better than the leaving groups here?
The head resonance.
Yes. Resonance increases the stability, making that the better leaving group. Now, why are the negative charges on oxygen a better leaving group than the negative charge on nitrogen?
You have the negative charge on a more electronegative atom.
Yes, that's right. So this leaving group ability here, right, it could be based on different factors. Electronegativity is a factor, and then resonance is a factor as well, right? And also form or charge as well. Like this oxygen with a -2 charge is very unstable. We do not want like a lot of form or charges like that. That's very unstable.
Yeah.
Right. So that's the first factor. The second factor is going to be about the electrophilicity of the carbonyl carbon. And I'm going to color code the electrophilic carbonyl carbon in blue like this. And see how reactive it is. The more positively charged it is, the more reactive it is, right? We see that the acyl chloride has the biggest positive charge because this halogen here is going to have poor resonance with the carbonyl. It's not going to donate its electrons as much due to two reasons, right? Due to its high electronegativity, it wants to keep its electrons, so it doesn't really want to do resonance. And also, if it's a bigger atom like chlorine or bromine, it has poor p orbital overlap. So if it does not donate electrons very well with the carbonyl is going to remain positively charged. It's not going to gain electrons, right? Now, if we look at the very right here, this full negative charge here is very angry, right? It's going to want to do resonance a lot with that carbonyl. And because of that, the partial positive charge of this carbon here is very small, right? Now, if we compare the resonance of the oxygen and nitrogen here, nitrogen is less electronegative than oxygen is. So it's more willing to give up its electrons and do resonance with the carbonyl like that. So because of that, the partial charge on the nitrogen is smaller than the partial charge on oxygen because there's more resonance going on here in the amide.
Yeah.
Right. Now, the difference between the alcohol, OR, and the carboxylate here is that this oxygen here, its resonance is being split in half between two carbonyls, right? Because it can do resonance with the left carbonyl or the right carbonyl. And because it's split in half, the carbonyl here on the left that I color-coded is not gaining as much electrons as it is compared to this carbonyl carbon and this carbonyl carbon, because the oxygen pair of electrons here is fully focusing on that carbonyl to do 100% resonance with that carbonyl, whereas the anhydride here, its resonance is split in half because of the other carbonyl here. So there's competition of resonance there, right? So that's another reason that describes the reactivity here. Now, like I said earlier, the top two here, the acyl chloride and anhydride, they do not require an acid or base catalyst or heat, the delta symbol, to do reactions because they're the top two most reactive derivatives, right? So they can react with neutral conditions.
Oh, okay.
Can react with neutral conditions. So,
okay.
for example, if you have an acyl halide or anhydride, if you just put neutral H2O or neutral ROH in there, the reaction will go through, right?
Yeah.
But if you have a carboxylic acid, right? Like if you put a neutral nucleophile there with a carboxylic acid, no reaction would happen because a carboxylic acid or ester or amide or carboxylate, they're not reactive enough to react with that neutral molecule. You need to add like some sort of acid or base catalyst with heat to make the reaction go through with these lower reactive derivatives. Yeah. Now, some of these reactions can work in acidic conditions, basic conditions, both, or only one, right? And I'll give you an example of that one reaction right now. Let's say that I have this carboxylic acid here, this very basic carboxylic acid, and I want to convert this into an ester. There's a very specific name of this reaction.
Fisher esterification.
Yes. And Fischer esterification here can only happen in one of the conditions, acidic or basic conditions. Which one would it be?
I think it was acidic.
Yes. So it's going to be the neutral alcohol, which is the OR group of the alcohol. Is going to be the OR group of the ester right there. And because this is in acidic conditions, we're going to do H2SO4. So that's the reagents right there. The reason why it cannot happen in basic conditions, right? Like the reason why it's not going to be like these arrows here with the OR minus and then the solvent right there is because if this is a strong base right here, what is going to happen instead? Like if we have a strong base and a strong acid.
It's just gonna deprotonate.
Yes. So I'm gonna put an X right there because it's not gonna form that. It's gonna deprotonate the carboxylic acid to form a carboxylate instead. That's what is gonna be formed instead of this ester right there. Right, so that's why carboxylic acids here do not work well in basic conditions. Because if you put that carboxylic acid through any base, any strong base, it's gonna get deprotonated to get to the carboxylate instead. So it's just gonna do a simple acid-base reaction, not a nucleophilic acyl substitution reaction. Right.
Yeah.
So if you look through all those like reactions that you learned, like ester hydrolysis, saponification, anhydride reactions, they're all gonna follow like this reaction right here, right? Yes. Any questions on that, Wiley?
No.
That's good. That's good.
Makes sense.
Yes. Let me go check Kelly's practice quiz that she sent me so we can work through them. Hey Layla, how is the final material for 118B going so far for you? Are you getting overwhelmed yet? Like, what are you on? Are you on chapter 17 or chapter 18 for lecture? Or are you caught up with lecture?
Yeah, I'm like trying to understand all the reactions of the aldehydes and ketones right now, but it's like so many different ones.
Yeah, it is. Yeah, like with the hemiacetal, imine, enamine, there's a lot. Like Wittig reaction, Bayer-Villiger oxidation.
I don't think he's gone into the other ones yet, but
Oh, okay. But just imine and enamine, like that's the last thing you remember?
yeah.
Okay. Sounds good. Ooh, is this the practice quiz for this week's quiz, Kelly?
It is, but it's not made by my professor.
Yes. This is a very Levens type quiz. I see. Right. A lot of vocab questions here. A lot of reactions. A lot of synthesis. Yeah. This is a very Levens formatty quiz right here. Right. Yeah. Did you have a chance to work through this practice quiz?
No.
Oh no. Okay.
I was trying to understand lecture first, but didn't work out.
Yeah. Have you been going to lecture or have you been skipping and watching the recording if it's recorded?
I go, but it doesn't really stick with me. So then I watch it and that still doesn't stick with me. So then I just sit there and I stare at it.
And cry.
Yeah.
Okay. We could work through the first problem if you learn about this reaction. Did you learn about alcohols and HX reaction yet?
Yes.
Okay. So before we go over that problem though, let me explain to you that reaction in general. So if I have, let's say, this molecule right here with an alcohol and I react this with HBr. Let me see what you know so far. It's okay, just let me know if you don't know what's gonna happen in the first step. What do you think is the first step? When we have a very strong acid, HX, and this molecule here, what's gonna happen in the first step?
Magic.
Yes, magic's gonna happen where like if we have a strong acid right here, we have to look for the most basic atom in this molecule, right? the most basic atom in this molecule is going to be oxygen of the alcohol right here. Right, so I'm going to draw out the HBr like this, and I'm going to draw out the bond out explicitly between H and Br to show this mechanism very clearly. One of the pairs of electrons on oxygen here is going to attack that hydrogen right there. And the reason why is because this hydrogen here is partially positive, since it's attached to an electronegative atom right there. So then we're going to kick out that leaving group bromine to give me this intermediate right here. This OH is going to become OH2 plus with the full positive charge. This oxygen here gained a hydrogen from the HBr, and for Levin's quiz, she wants to draw out the leaving group that left as well for the mechanism. Like, she wants you to draw out all leaving groups, all side products that gets formed. Does that make sense so far, Kelly? Like that first step that we just did? Like, any questions on why things happen like the way they did?
Hold on. My hands are slow.
No, it's okay. It's okay.
So the bromine is the good leaving group because it's basic?
The bromine is the good leaving group because when you think about leaving group, right, that term is going to basically mean that any group that leaves in the mechanism, and it's going to be a good leaving group if it can handle like the pair of electrons it gains with the leaving action, right? Because we see that the bond right there represents 2 electrons. The 2 electrons in this bond right here are going to go onto the bromine, giving that bromine a full negative charge. This bromine here can actually handle that negative charge very well because it's highly electronegative, right? Like, the halogens in the periodic table are like the most electronegative atoms we have, so they can handle that negative charge very well. So they're not very unstable. They can actually handle that negative charge, making them a good leaving group.
And then the hydrogen attaches to the OH.
Yes, and that becomes OH2 plus.
Because it has a positive charge?
The hydrogen here, right? If I were to like make it more clear for you, the OH is right there. That is there originally is going to be in blue. This H of the HBr is going to be in yellow. This OH2 plus here, right? The blue hydrogen was always there. Nothing happened to that blue hydrogen. This is the yellow hydrogen that created this new bond to that oxygen right there, and that new bond came from that red pair of electrons right there. The 2 electrons in this bond right here, right? That's the new bond right there. That new bond came from that pair of electrons right there, which is why we see that this oxygen here has only 1 pair of electrons now. It no longer has 2 pairs of electrons because it used 1 of its pairs of electrons to create that new bond between the oxygen and hydrogen when it grabbed that hydrogen right there. And are you familiar with calculating 4 more charges from Gen Chem or 118A, or like the previous like units in 118A, Kelly?
I remember doing it, but I don't remember exactly what was added. Yeah.
So to calculate 4 more charges of an atom, right? This is the equation I use. Well, this is what I think about. It's gonna be the number of electrons an atom wants, right? And that's based on the periodic table and what group the element is on, minus number of electrons an atom has, right? So this oxygen here, it's on the 6th column of the periodic table, meaning that it wants 6 electrons to itself, right? But when we count how many electrons it has to itself, it has that 1, 2, 3, 4, 5 electrons to itself. Right? This bond here has 2 electrons, but it's shared, right? 1 electron belongs to the oxygen, you could think of it like that. The other electron belongs to this carbon right here. So when we calculate how many electrons this oxygen has to itself, it has 1, 2, 3, 4, 5 electrons, but it wants 6 electrons. 6 minus 5 is positive 1, right? So it has a positive formal charge because of that formal charge thing. So you could, like, the more you do this, the more like common patterns you're gonna pick up. When oxygen has 3 bonds, right, that's gonna be most likely positively charged. When oxygen has one bond, it's most likely negatively charged. When oxygen has two bonds, it's most likely neutral. Like that, right? So you have like two oxygens, a bond with, this oxygen here with two bonds being neutral, this oxygen being negatively charged with one bond, and because this oxygen here has three bonds, it's positively charged. So you could think of it like that if you wanted to, like the common patterns, but it's best to think about like the formal charge equation first, and then the more practice you do, the more patterns you pick up. Right. Does that make sense so far, Kelly?
So the oxygen wants to be positive charge?
It does not want to be positively charged because it's unstable with that positive charge, but it has to have that positive charge, right? Because it has three bonds, 1, 2, 3, and a pair of electrons. So it's forced to have that positive charge right there.
Okay.
Right, but don't think about it like it wants to have that positive charge, because it's less stable in this form than it is in this form, right? This neutral form right here, when it's neutral with two bonds and two pairs of electrons, it wants to be in this form instead. Right, but it's forced to become positively charged because of the strong acid here. The strong acid protonates this OH to become OH2 plus, like that. Yes, Khadija.
So the acid forced the oxygen to take another hydrogen.
Yes. Right. The acid here forced the oxygen to take another hydrogen, because this acid here is the acid, this OH here is the base. So when the base gets protonated, it's forced to get another proton, hydrogen.
Okay.
Yeah. Yes. Khadija, you had a question on this problem? Hi.
Not this problem. 118B.
Yeah, 118B.
Yeah. So I just had 3 questions. Right now we're learning about aldehydes and ketones, and I wanted to know what reagent like we use to go from like a secondary OH to an aldehyde, because the professor in lecture, he only showed us how to get from a primary alcohol to an aldehyde, so I didn't know like what reagent. Do we use the same one?
A secondary alcohol like cannot be converted to an aldehyde.
Oh.
Right. This is the end of 118A. Like, do you remember when we learned about oxidation and reduction of alcohols? Like, we had a primary alcohol. This is what Kelly's learning right now. Secondary alcohol, and let's say tertiary alcohol. There's 2 oxidizing agents that you learned in 118A: PCC and Jones. Does that sound familiar?
Yes.
Yes. Right. So it does matter what you use for the primary alcohol, because it would change what you use. If you use PCC, what would the primary alcohol turn into?
If we use PCC for which one?
The primary alcohol.
Oh, primary. I think we will get an aldehyde.
Yes, we'll get an aldehyde because that's a weaker oxidizing agent. So we're gonna weakly oxidize the primary alcohol to the aldehyde. But if we use a stronger oxidizing agent in Jones, what would the primary alcohol turn into?
Is it a ketone?
Not a ketone.
Wait. Let me.
Yes. What another functional group?
Okay, so if it's gonna be carboxylic acid.
Yes.
We're doing it twice or something.
Correct. Because we're oxidizing the primary alcohol, right? And if you look at this blue carbon right here, oxidation, you could think of it in 2 ways. You could think of it as gaining bonds to oxygen atoms or electronegative atoms, right? Or you can think of it as the loss of hydrogen atoms. So this blue carbon right here has 1 bond to oxygen and 2 bonds to hydrogen. If we use a weak oxidizing agent, we traded 1 hydrogen bond with another oxygen bond, because this form here has 2 bonds to oxygen and 1 bond to hydrogen, right? So it lost 1 bond to hydrogen and gained 1 bond to hydrogen, so oxygen, right? But when we use the stronger oxidizing agent, we traded 2 of the hydrogen bonds to 2 oxygen bonds, because now this carbon here has 3 bonds to oxygen, right? It lost its bonds to hydrogen to gain 2 bonds to oxygen. That's why this is a stronger oxidizing agent right there.
Got you.
But now it doesn't matter if you use PCC or Jones, you get the same exact answer for secondary alcohol, which would be what functional group?
Wait, give me a sec. So tertiary, if we do tertiary, ketone?
Yeah, ketone, yes, with a secondary alcohol, not tertiary alcohol.
Yeah, secondary. Yeah.
Right. We can get a ketone because we can only trade 1 hydrogen to 1 bond to oxygen, right? On that blue carbon. We would not get something like this because there's a very big problem with this structure here.
Yeah, because like carbon has 5
Yes.
bonds.
That breaks the octet rule.
Okay.
So that's why we won't get this weird looking structure right there. But now, if we look at the tertiary alcohol right here, does it have any hydrogens to trade in for a bond to oxygen at this carbon right there?
No.
No, right. So there's gonna be no reaction.
Oh, okay, cool.
Yeah. Mm-hmm. Yes.
And then that's the same reason why for the primary alcohol?
Yes. Mm-hmm. For the primary alcohol, it has 2 hydrogens to trade, right? If you only want to trade 1 hydrogen, like do weak oxidation, don't oxidize all the way. You use the weak oxidizing agent, PCC, to stop at the aldehyde. But if you want to trade both hydrogens to an oxygen, you want to use the strong oxidizing agent Jones to get to the carboxylic acid. And Jones here could be in helix class, CrO3, H2SO4, water. You could also see it in the form of Na2, Cr2, O7, H2SO4, water. A big signal of it is going to be chromium and a lot of oxygens. Chromium and a lot of oxygens. That's Jones right there.
Got it. Wait, is that a Na2Cr2O? 7? Okay, got it. Yeah. They both do the same job.
Yeah, right. They both do the same job. They both would be a strong oxidizing agent.
Okay, and then the reason why we don't do secondary, what was the reason again?
Secondary alcohol or tertiary alcohol?
Wait, I forgot my. Wait, so secondary alcohol to aldehyde.
We cannot form an aldehyde because if we make a carbonyl here, right, by trading in this hydrogen bond to the oxygen bond right there.
Yeah.
This carbonyl here is attached to 2 R groups, right? So this is automatically a ketone. It cannot be an aldehyde because an aldehyde would have to have a hydrogen right there, right? So when we traded in this 1 hydrogen to this 1 bond to oxygen right there, we stop at the ketone. We cannot stop at the aldehyde.
I see what you mean. It's just because it doesn't have enough hydrogens.
Correct. Whereas the primary alcohol here, when we trade in 1 bond to hydrogen with a bond to oxygen, we still have that 1 hydrogen right there.
Gotcha.
Making this an aldehyde, right? But this right here has 2 R groups from the secondary alcohol. There's no more hydrogens. We only have 1 hydrogen there.
I see. Okay, thank you so much. And then is it okay if I ask my other 2 questions just so we finish 118B stuff?
Yes, if it's quick, I could answer it now.
It's quick.
Yeah.
Yeah. Okay, cool. So I wanted to know what reagents we use to go from an alkyne to an aldehyde.
Alkyne to an aldehyde. Yes. So that is gonna be midterm 2 material. It cannot be any type of alkyne, right? Because there's 3 types of alkynes that you can have. You can have a terminal alkyne, right? And you have an internal alkyne, but there's 2 types of internal alkynes. There's symmetrical internal alkyne, and there's an asymmetrical internal alkyne. And if you want to create an aldehyde from an alkyne, you can only do that with a terminal alkyne. You cannot create an aldehyde from an internal alkyne, like either symmetrical or asymmetrical, right? So I'm gonna give you an example of a terminal alkyne like this, meaning that the alkyne here is at the terminal end of the molecule, right? It has 1 hydrogen like that.
Yes.
Now I'm gonna show you the intermediate of this reaction, and this might make things more clear. So let's say this is atom 1, this is atom 2, this is atom 1, this is atom 2, and on atom 2 we have this ring right there. Notice how I added an alcohol at the less subcarbon, atom 1. That's the antimark reaction.
Antimark, yes.
What reaction do you know that adds alcohol to the antimark carbon?
Ooh, putting me on the spot.
Yeah.
Okay, so oh my god, this is so hard. Okay, I know that it has something to do with water. Right?
Yeah, yep.
Okay. And then is it acid?
Yeah.
Acid or base?
So I'm gonna give you 2 names.
Okay.
Hydroboration oxidation versus oxymigration demercuration.
The first one.
Yes, first one, hydroboration oxidation.
Yeah,
and for
'cause
alkynes specifically, it's not BH3, it's the CY2BH, THF, second step, H2O2, NaOH, water, which would add alcohol on the less subcarbon. But we don't stop here as the final answer, because what is this functional group you see right here?
That's an are you asking if it's an enol or if it's
It's an enol.
Oh, enol, yeah, it's an enol.
And
so you have to tautomerize.
Tautomerize, yes, into carbonyl.
Yes.
Like this.
Yeah.
And that's an aldehyde right there, because there is an invisible hydrogen right here, which is that right there, right?
Yeah.
Yeah. So that is how we create an aldehyde from an alkyne, but it has to be a terminal alkyne. Like if this was an internal alkyne, we would create a ketone with this reaction.
Okay, so the only difference between the two is that this one aldehyde and the other one is ketone.
Yes.
Okay.
Because hydrogen oxidation looks for the less subcarbon, the anti-mark carbon. Internal carbon has no less subcarbon. They're both equally substituted.
Okay, cool. And then I don't know if this will take time. You can let me know. Like I can wait. That's totally fine. But I wanted to know if you could show me how to like react the ketone with the lithium like LiAlH4 THF, and then we also do an H+ workup.
So let's say we have something like this. This is gonna be very similar to an organometallic reagent, and this is what Kelly is gonna learn too at the end of 1A. We have an electrophilic carbon here, that partial positive carbon-on-carbon, and when you see lithium, Li, think of that as MgBr. Right, it's gonna do the exact same thing.
Okay.
The carbon directly attached to Li or MgBr is our nucleophile, the partial negative charge. So when this star attacks the dot here, we're gonna make a new bond between the star and dot. The lithium and MgBr dissolves away in the solution as a result, but there's a problem here of that carbon. When that carbon gains a bond, it's gonna have 5 bonds. 1, 2, 3, 4, 5. So to conserve the octet rule, we have to pop that double bond onto the oxygen like that. Right? And that's gonna give us this tetrahedral intermediate right here. This is the dot carbon right here. This is the single bond O- that came from the double bond O. This is the new bond between the star and dot from that attack. The star atom here, right, is part of a ring. So I'm gonna draw that right here, right? It's not like this right here. Right, a lot of people would have drawn that.
That's what I would have drawn.
Yeah, because this is the dot carbon, this is the star carbon, that's the new bond between them. This star carbon here is not out of the ring, right? Yeah. It's part of a ring. This would be the answer if your starting material, your gradient reagent, was like that.
Got it. That's what's so confusing. It's like when do you make like the extra? I think it's just really confusing when to add the extra, like the extra C.
Right, the extra C, and when to like make it part of a ring like that.
Yeah.
Exactly. That's why I do the star and dot technique, because that keeps track of every group, and like that avoids doing that problem, adding an extra carbon or losing a carbon by accident,
Yes. No, I'm definitely gonna implement that.
Yes, that's good.
I think that's it, right?
Yeah, and then the second step, acid workup, that would do.
Oh yeah, OH. Okay.
Convert the O- to OH neutral. Yeah.
Okay, cool. Thank you so much. I really appreciate it.
Yep, of course.
Thank you. Have a good night.
You too. Good night.
Take care.
Take care. Okay, so Kelly, did this reaction look familiar to you? The organometallic reaction, or this oxidation stuff with alcohols? Because this is the very end of 1A right here.
The organometallic was
like gradient reagent, like MgBr.
Yes.
Okay.
That thing.
Yes. This star and that technique right here, I want you to implement this right away as soon as possible, because you're gonna see that when you do a lot of practice problems, or your classmates when they do it, they're gonna mess up a lot on like connecting the pieces together. They're gonna either add an extra carbon or lose a carbon. Remember, Wiley, when you learned about organometallics last semester, like sometimes you added an extra carbon by accident when you learned about this reaction. I remember like when you sent me your answer for one of the practice problems I made you. Yeah. Does it look like doable though, Kelly? Like does the mechanism look understandable?
No.
No. Okay. We'll worry about that later then. Let's go and finish what we started here. Does this make sense though? Like what we just did right here earlier, like when we protonated the OH with the strong acid to create OH2+ right there.
I sort of forgot it, but then I remembered it.
That's good. That's good. This neutral OH right here, right? Think of that as a bad leaving group. When we protonated it to become OH2 plus, this is now a good leaving group. Right? The reason why this is a bad leaving group is because imagine when it leaves, it's gonna leave with a -1 charge. So before it's neutral, right? 0 minus 1 is -1. So this is gonna have OH minus as when it leaves, right? That's unstable. But when this leaves, it's gonna leave as water, neutral water, right? Because +1 minus 1 is neutral, 0. So that water there is stable. That's why that's a good leaving group. So now, are you familiar with SN1, SN2, E1, E2 reactions?
I try.
I try. How'd you do on that quiz? Like, did you have that quiz on SN2, SN1, E1, E2?
That's the one that I went to late.
Oh, that's the one you went to late, and you like somehow managed to finish in time still, right?
Somehow.
Yeah. Did you get your grade back for that one?
Yeah.
How was it? It's
average.
Average? Okay. Wait, hey, that's pretty impressive. Like,
I don't know. I got
like
the
this...
whole. There was one question that was like, "Oh, you
being
had to
late?
use E1," but then I messed up because my brain confused primary carbon and secondary carbon, and it thought it was no reaction.
Oh, did you use that chart like with the SN1, SN2, E1, E2 chart and the nucleophile base and the substrate primary, secondary, tertiary chart?
And I saw it wrong.
Oh my god. Dang. So from this point here, right? If we have a good leaving group like this and we're an aqueous solution, think of this as an SN1 reaction. SN1 reaction, right? What's the very first step of SN1 reaction when we have a good leaving group? What happens to the leaving group?
The leaving group leaves?
Yes, the leaving group leaves to form what kind of intermediate? This is a very special name of this intermediate, and this is very important. Keep that intermediate in mind when you go to 119B.
Carbocation?
Right? Yes, carbocation intermediate. That's very important. And whenever you have a carbocation intermediate, what do you always have to look out for?
Wait. Is the black one the carbocation or the leaving group cation?
This bond right here, right? It's 2 electrons are gonna kick off onto the oxygen, creating H2O. So that black bond right here, this wedge bond, is no longer there. It is now here, right? As a pair of electrons on that oxygen.
So the new molecule that you drew is the carbocation.
Yes, this carbon right here. This carbon specifically is the carbocation.
Oh, that's the
Yes. Because that carbon there lost the bond, right? Like if I color code that bond in green, color code this carbon in green for you, that's that carbon right there. There is an invisible hydrogen right here. So right now this carbon here is neutral because it has 4 bonds, right? It has 4 electrons to itself. It's on the 4th column of the periodic table, so it wants 4 electrons to itself, and it has 4 electrons to itself. 1, 2, 3, 4. 4 minus 4 is 0. The hydrogen is still there, right? So when we calculate the formal charge of this carbon now, it has 1, 2, 3 electrons to itself. 4 minus 3, +1. So that's why this carbon here has a positive charge, right? Another way that you could think about it is that it's losing electrons when this leaving group leaves, right? It lost the bond, making that carbon positively charged. And when a carbon has a positive charge or a cation, we call this a carbocation intermediate.
Carbocation is talking about only the carbon?
Yes. Only talk about the carbon. If you say carbocation intermediate, you might like refer to that whole thing as the carbocation intermediate, but this carbon here is what is making that carbocation intermediate right there. That's the most important thing for carbocation.
Okay.
Right, but like, cause like this whole thing could be referred to as the carbocation intermediate. Right, but if you want to get specific into it, this is the carbocation right here, the carbon with the cation, the carbon with the positive charge.
Okay.
Yeah. And when you have that carbocation, what is that sneaky stuff a lot of students forget about?
It's very sneaky because I'm forgetting it.
Yeah, it's very sneaky. Layla, do you know the very sneaky step from midterm 1 material whenever you have a carbocation?
Rearrangement?
Yes, rearrangement. And it's either gonna be a hydride shift or methyl shift. Does that sound familiar, Kelly?
No.
No? Okay. Do you know about carbocation stability? Like primary carbocation, secondary carbocation, tertiary carbocation? Which one's more stable?
Primary?
Oh, okay. So let's go over that. Okay, let's go over that. So this is a methyl carbocation. This is a primary carbocation. This is a secondary carbocation, and this is a tertiary carbocation. We will not worry about allylic carbocation or resonance carbocation yet. That's gonna be for what is in B next quarter. I'm gonna color code the carbons with the positive charge, the cation. The more substituted the carbocation is, the more stable it's gonna be. Right, so stability would increase from left to right here, because this carbon here has more friends around it, right? And its friends are gonna be considered the R groups. This is the less stable carbocation because it has 0 friends. It has 0 R groups. This carbocation here has only 1 friend. This carbocation here has 2 friends. So the more friends the carbocation has, the more stable it's gonna be.
Wait, for the second one?
This one right here or this one right here? Sorry.
The left one.
The left one, this one,
Is the carbocation on the middle or the right one?
It's gonna be the right one right here. This, oh shoot, why did I color code that? It's weird. Yeah, nice catch, nice catch. It's gonna be this carbon right here. Yes, yes. Thanks for catching that.
So it's more stable as it goes to the right because it has more friends.
Yes, it has more friends. More friends.
Okay.
But do not like put that as the explanation for if this was an explanation problem. This is gonna be known as hyperconjugation.
Oh.
Does that sound familiar?
Yeah, because I didn't know what that was when I was doing my practice set.
Hyperconjugation, right? What that basically means is that the R groups here, you're gonna learn this later, they're gonna be electron donating groups. So they're gonna inductively donate electrons towards the carbocation. Right? And I'm gonna abbreviate electron donating group as EDG. So these EDGs here are gonna naturally, inductively donate electrons towards the positive charge, which makes it more neutral, more stable. If we look at this methyl carbocation here, there's 0 R groups, 0 EDGs. So this positive charge is extremely unstable, right? Because you know how when we learned about resonance structures, the most major like stable resonance contributor is the one with 0 formal charges, right? We do not want formal charges at all. Like when you see formal charges, think of like instability, unstable, right? This positive charge here is, you could say, neutralized. It's becoming more neutral by these friends right here, donating electrons to it. Whereas the secondary carbocation here, because it only has 2 groups, 2 EDGs, there's only 1 group donating electrons to it. This primary carbocation here only has 1 group donating electrons to it. The more groups the carbocation has around it, the more stable it is, because the more neutral it's gonna get, the more electrons it's gonna gain by its friends around it. It has a bigger support group. And that's hyperconjugation right there. Right? Okay. Now this is the stability arrow, right? But the reactivity arrow, wait, actually no, that was I'm not gonna say that. So just keep that in mind, okay?
Okay.
Okay. Okay. So now, what kind of carbocation right here do we have? Primary, secondary, or tertiary?
Wait, more friends means more stability.
Yes, more friends, more stability. More R groups around, more stable. But what carbocation is this?
Secondary?
Secondary, yes, because it has 2 other carbons attached to it. 2 R groups. The R group and this R group right here. Whenever you form a carbocation intermediate, look to the left and right of it and see if it can become more stable. So if this is a secondary carbocation, let's look at this carbon and this carbon here. Let's say this is A, this is B. At what position can it become more stable in? A or B? Or if it can?
Huh?
Like, can we, like, let's imagine a carbocation at A right here, and let's imagine a carbocation at B right there. Which one is more stable? Which one looks more stable to you?
Oh, B.
B, yes. So we want to move the carbocation there, and we can actually move that carbocation right there. Right? This is the rearrangement step here. But when you draw the mechanism, right, do not draw that arrow. Do not draw the positive charge moving towards that carbon right there. Right? Because when you draw arrow, right, like what does the arrow represent? The movement of what?
Electrons?
Electrons. There's 0 electrons there. There's no electrons there. That's an empty p orbital.
Oh.
Right? But what we're gonna do instead, right, is we're gonna do this. We're gonna draw out this invisible hydrogen right here and shift that bond with the hydrogen over to the carbocation.
Huh?
So this is a hydride shift right here. Hydride shift, where I'm moving this whole bond with the hydrogen over to this carbon right here. So this carbon here has that hydrogen right now, right? And becomes neutral as a result. Because this green carbon right here did have a hydrogen before, which I'm going to color code as blue. That is going to be this blue hydrogen with the blue bond right there. I just color coded. So this was always there, right? It was invisible before, but I just drew it out right now. And because it had 3 bonds, it's positively charged. When this bond with the hydrogen moved over to that carbon right there, we created this like new bond to hydrogen. And because this carbon here has 4 bonds now, it's now neutral, right? 1, 2, 3, 4. But the methyl group here that was dashed before becomes positively charged because it lost this bond, right? It now has 3 bonds. 1, 2, 3. It's positively charged.
Okay.
Now, this reaction was favorable because we converted a secondary carbocation to a tertiary carbocation. Right there.
I feel bad that everyone just laughed.
No, it's okay. It's okay. It's okay. I think they had their help when I went over 1SNB questions because Layla was in 1SNB. So I went over 1SNB stuff here with the alkyne and organometallic with the ketone and oxidation here as well. And Wiley, I helped him earlier. So I think he got his help as well. Yeah, so it's okay. Don't worry.
Okay.
So does this make sense so far on like how we got to this intermediate right here?
So the hydrogen was like bye-bye to the carbocation on the left. And then no. Okay.
The carbon here gained the hydrogen, so it's like hello, not bye-bye.
No, the yellow one.
Oh yeah, on this carbon right here.
Yeah, it said bye-bye.
Yes, it said bye-bye to this carbon. Yes, and because that carbon lost the bond, it's positively charged now.
Why did it say bye-bye?
Why does it say bye-bye?
Yeah.
Because it wants to convert this secondary carbocation to a tertiary carbocation. Which one is more stable?
Tertiary.
Yes, tertiary. That's the reason why it goes bye-bye and goes to that carbon right there to be able to get this happy, stable carbocation. What is the hybridization of this carbon right here, Kelly? Like, is sp, sp2, sp3?
Give me 10 seconds. sp2.
Yes, sp2 hybridized. And what is the shape of that? Is it tetrahedral, flat, planar, trigonal planar, linear?
Trigonal planar?
Trigonal planar, yes. So it is flat and planar. I'm gonna bring in the Br minus that we kicked out earlier as my nucleophile. When we attack this carbocation right there, like when we attack this carbon right here, the Br can attack on the top side or the bottom side. Right, and that's gonna give me a wedge or dash product because one of my products here is gonna have a wedge bromine when it attacks on the top side, forcing the methyl group to become a dash, or if the bromine attacked on the bottom side, the bromine would become a dash, forcing the methyl group to become a wedge. Right, so these are our 2 products here. Right, instead of drawing out that whole thing, you could have drawn like plus enantiomer. Or this plus minus right there.
That?
Enantiomer is a did you learn about stereochemistry yet, Kelly? Like enantiomers, diastereomers, mesomolecules.
We did, but I still don't get it.
So an enantiomer is when all chiral centers flip from R to S or S to R. Right. So this is the only chiral center we have right here. That red star that just starred. That's the only chiral center in this molecule right here. You notice how this molecule here has the same chiral center, but it's flipped. Like, well, I want you to figure out, is this R or S? This chiral center right here. How would you figure that out?
Wait. 1, 2, 3.
Nice. Because the 1 is bromine, 2 is this group, 3 is this group, and going this way clockwise is R, and our lowest priority group here is a dash, so we keep it as R, we don't flip it. Right? What about this one?
1, 2, 3 S.
So 1, 2, 3 same way, but it looks R, but because our lowest priority group here is a wedge, right? We don't keep it as R, we flip it to S. Right? And notice how this chiral center here flipped from R to S. Every single chiral center in this molecule here changed or flipped, making these two molecules enantiomers of each other.
What if it was only, like, if there were 2 chiral centers and only one of them flipped? Then...
And the other ones stay the same?
Yeah.
That is diastereomer.
So diastereomer is when not all of them flip.
Diastereomer is when some of them flip and some of them stay the same.
So it doesn't matter how many,
yes.
as long as it's not all.
Correct. Because if a molecule has, let's say, 5 chiral centers, if 4 of them change and one of them stays the same, diastereomer. If 3 of them changes, 2 of them stays the same, diastereomer. If 2 of them changes and 3 of them stays the same, diastereomer. If 1 of them changes and 4 of them stays the same, diastereomer.
Okay.
Right? So it's only some of them that change and some of them stay the same. If all 5 chiral centers change, they would be enantiomers. If all 5 chiral centers flip.
By flip, do you mean like the whole molecule flips, or just...
Oh, no, not the whole molecule, the chiral center.
So like, if you just like go flip, but then wouldn't that all of them flip?
What do you mean all of them flip?
Like if you had the 2, like 1 wedge and 1 dash, and you did a little flip around the chiral center.
Oh yeah, are you thinking of flipping the whole molecule? That's another way that we talk about flips as well. But I'm talking about flipping the chiral center from R to S or S to R. Right? I'm not talking about flipping the whole molecule, like a page or a book. Right? Because there's 2 ways that you hear flips in OChem. Like you flip the whole molecule upside down, and that would maintain the same stereochemistry, or you flip the chiral center from R to S or S to R. So in this case, I'm flipping the chiral center, not the whole molecule.
So by flipping the chiral center, you mean you change the wedge and the dash on just the chiral center?
Yes.
But then if you flip it, if there were multiple chiral centers, and you flipped all of them, then wouldn't they all be flipped?
Yeah, they would, and they would be enantiomers at that point.
Regardless of R and S?
R and S would be flipped because all the R chiral centers would be converted to S. All the S chiral centers would be converted to R when you flip those chiral centers. When you flip those wedges and dashes.
So if one is an R and one is an S, that means it's a diastereomer?
Like if one molecule had an R and one molecule had an S, those are enantiomers. But if a molecule has an R and S in that order, and another molecule has S and S in that order, these are diastereomers. Because this set of molecules here only has one chiral center, everything flipped, R to S. This one here, the first chiral center changed, the second chiral center stays the same. Those are diastereomers, right?
So for the right version, if it was R and S and then the second one was SR, that would be an enantiomer?
Yes. In that specific order, because the first chiral center flipped from R to S, second chiral center also flipped from S to R. So these two would be enantiomers of each other. Right? Enantiomer there, diastereomers here, enantiomers there, like that.
Do you know an example of a diastereomer?
Another one?
Yeah.
Yeah. So another one would be something like this. Let's say we have, in this order, like that.
I don't think my brain is properly conveying my confusion.
So let's say we have the carbocations in this order, like 1, 2, 3, 1, 2, 3. Which ones changed?
2 and 3.
2 and 3. Which ones stay the same?
1.
Yeah. So did all change?
No.
No. Some of them change. Some of them stay the same. Diastereomers.
That's not where I'm confused about.
What are you confused about?
So if you have the little molecule drawn out, like and you have 2 chiral centers, and you flip just the chiral centers.
Like, are you talking about 2 chiral centers? Like, let's say this one and this one. OH, BR.
Yeah.
You want to flip both of them?
Yeah.
If you flip both of them like that, what would they be?
Wouldn't that be an enantiomer?
Yep. Enantiomers, yes.
But then how is it so that only one of them is flipped? Like for diastereomer.
Yeah, so it could be bromine or alcohol. Like, let's say we have the same thing right here. There's 2 diastereomers of this structure. One diastereomer would be this. Another diastereomer would be this. Right. This is a diastereomer to this. This is a diastereomer to this.
So you have 2 different molecules that just have the same chemical formula, and you just changed it. It's not like you're doing something to the left one to get the right one.
No, you're not. You're not changing up the geometry or the regiochemistry of it. You're just changing the chiral centers, the stereochemistry.
But you're not altering the stereochemistry of the left one.
Like this one right here?
Yeah.
We are. Like, for the diastereomer, we're changing this chiral center for that diastereomer. For this one, we're changing this chiral center to get this diastereomer here. Like, the chemistry is altered, but the regiochemistry is not altered.
I'm just gonna take a picture of it and sit on it.
Okay.
It'll come to me one day.
Yes. We'll continue tomorrow.
Yeah.
Yes. Because what do you mean by not altered? Like.
Because I thought whenever I got an enantiomer diastereomer problem and they asked, "Oh, is this an enantiomer or whatever," I thought that they did something to the left molecule, and they're like, "Oh, like I thought they wanted me to flip it and see if that would be the enantiomer
no,
or the
you don't do anything.
diastereomer."
You don't do anything to the molecule. You just analyze the chiral centers.
So you just have the 2 and you go, this is different from this one, or this is the same as this one.
Yeah, you just do that. You don't have to draw anything. You don't have to flip anything. They flip it for you if it is flipped, and then you just identify it. You don't do anything to the molecule.
That's great.
Yeah. Like, these ones, I just giving you examples, but they won't have you draw out things unless they say draw in diastereomer this. But the most likely going to give you 2 molecules, and they want you to analyze the differences between those 2 and the similarities between those 2.
Oh, okay. Can I just ask one more question?
Yeah.
You know how when you were explaining the 118B thing and the organometallic?
Yeah.
When you wrote above the arrow, like 1, 2, whatever chemical thingy-majiggy, what was the... hold on. I took a picture of it.
Yeah.
Do you have your phone?
Yeah. Let me go get my phone.
I just realized that you sent me a text. Oopsies.
You ghosted me, Kelly. How could you?
I'm sorry.
What the heck, Kelly? Oh my goodness.
It was a crazy day yesterday.
You had a long day yesterday?
I woke up at like 5:50
p.m. or a.m.?
a.m.
5:50 a.m. yesterday? Oh my goodness.
After like 4 hours of sleep, and I went to a vaccine clinic.
Dang. And then you worked or volunteered, and then you rode horses.
No, I didn't even get to ride horses. I came back and I tutored my student.
Oh my God. Like, is it online tutoring?
Yeah.
Like through Zoom? How do you do Zoom as well, or Google Meet, or
Just Zoom.
Zoom? Oh my gosh.
But
Wow.
no, on Saturday, two of my students were like, "Are you okay?"
Like
They,
the
I could tell they were pitying me. They were like, "I think you can end early. We don't mind." I'm like, "No, your parents are paying for this."
Oh, oh my gosh. How old are your students?
High schoolers.
High schoolers. Oh my gosh. So they knew you were tired. They were like, Kelly is not okay right now.
No,
She is stressed out.
what their siblings, one of them asked what happened. He was like, with all respect, what happened to you? And I was like, so I got a little concussion. And he's like, oh, are you sure you can be doing this right now? And then his sister, the moment she came, she's like, are you okay?
Oh my gosh.
We can end 15 minutes early if you want. I'm like, no, it's
No.
fine.
Yes. They're gonna snitch on you, and then the parents are gonna be like, what are you doing, Kelly?
Exactly. So I gave her a little consult for 15 minutes instead.
How are your tutoring sessions like? Like, how do you organize them, or is it like random, like Q&A session for your private tutoring sessions?
I could show you.
Yeah, show me.
Wait, hold on. What would you like to learn today?
Oh, like are we role playing right now? Are you acting as
Yeah.
a tutor and I'm like the tutor? Oh,
Yeah.
I want to learn PEMDAS or
Okay.
yes.
Well, let's start with algebra 1.
Okay, algebra 1.
Let's go with
How to
algebra
find
1.
x.
Yeah,
how to
how to
solve for
find x. You can be like my yesterday student.
Oh, did you go over that? Like how to find x yesterday?
No, we were going over quadratics.
Oh, quadratic formula? Like what was that? Like something squared all over 2a?
Sort of.
Yeah, I forgot.
So I showed them the textbook. Oh, she was doing completing the square. So I just go, okay, so we have completing the square. You remember 2x and blah, 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 right? And then I have them do a little practice problem. Actually, no, I do the practice problem.
Oh, you
not
have the
them.
textbook? Oh my gosh. And then you can annotate with the whiteboard tool too, right? You guys do
Oh,
that?
yeah.
Oh my goodness.
I have to be like, oh no, wait, hold on. This is not my entire setup. My entire setup is not like this. Wait.
Do you connect your iPad too, or do you like do it on your laptop?
Oh wait, yeah, I do connect my iPad. Wait, hold on. Oh,
Okay,
wait, why am I drawing? Mirror extend.
I need help with this problem over here.
Sometimes my mouse refuses to work, so there's a buffer. Hold on. Where's share? There we go. And then I have a little sticky. Oh yeah, it's working now. Okay.
Oh wait.
So
hold on. Hello? Can you hear me?
Yeah. Hello?
Oh my gosh.
Hello?
Oh, I think my internet cut off. Am I back? Hello?
Oh, you're back.
Okay. Good.
Am I here?
Yes, you are here.
Okay.
You are here.
Okay.
Can you help me solve this equation? Or how to solve x, I mean?
Oh, how to solve for x with that equation?
Yes.
Okay. We are very below the level of this chapter. So we have.
Can you students do this? This solve this problem? They can do this? Okay.
So you have 2x plus 1 equals
wait,
9.
Are you on your laptop? Are you writing that on your laptop?
No, fine, I'll show you.
What?
Hold on.
How do you do this?
Hold on. You can check what kind of Asian I am now.
Oh my gosh, Chinese?
Okay, so here's my iPad.
What was that? Okay.
So I have this and I just go, ooh.
Oh my god.
And I just extend the screen thingy and I'm like, we're doing this, guys.
Yes.
Anyways.
That's so good. Oh my god.
First of all,
do you show your camera to your students as well? Like
I kind of have to.
Yeah. I know.
So first of all, we're gonna correct this. We're rewriting that.
Okay.
So whenever we write a problem, we like to put X on the left.
Yeah.
And anything with the X goes on the left. Just the number goes on the right.
Okay.
So what we first do is, because we want X by itself, is that we move all the numbers to the right side. And when we do that, we have to subtract or add.
Okay.
So in this case, I want to get rid of this +1. That was a bad circle. +1. So I'm going to subtract 1 from this side so that it goes away. But because I did that to one side, I need to do it to the other side as well.
Oh, why is that?
Because if you have 1 equals 1, I had to explain this yesterday too. If you have 1 equals 1 and you say add 3 to the side, you have 1 plus 3. And that doesn't equal 1 anymore.
Oh,
you have 4 equals 1, and that does not make sense.
Oh my god, I get it now. I understand it now.
Yeah, you have to add 3 to the other side as well.
Oh my god. That makes so much more sense.
I know. Astonishing.
Yes.
Why is my keyboard showing up? Oh, there we go. Okay. So we did that, and now we just subtract. So we have 2x equals 9 minus 1 is what?
9 minus 1 is 8.
And then since we already subtracted, we don't have anything else to subtract. There's nothing else to add. Now we have 2x, and that's 2 times x. So we have to get rid of the 2. Plus the opposite of multiplication.
Division.
So we would divide 2x by what to get just x?
2.
2.
Yes. It's
Gold
gonna be
star.
A clean number. That's so satisfying.
And you have to divide 2 to both sides. So you have 8 divided by 2 as well. So x equals 8 divided by 2 is what?
4.
4.
Yes.
Yay.
Oh my god, that looks like a 9, Kelly. What is going on here? Oh my god.
Literally what I did to my tutor so many times. He wrote like a 2 and I was like, is that a Z? Why is there a Z?
Yes. Do you tutor the high school students that were like that you went to, like the high school you went to, or some other high school?
One of them is my dad's former coworker's daughter.
Oh yeah, you told me about that.
She goes to a different school, and then I got 2 students. The ones that were pitting me are from my former tutor. He was like, I have a huge wait list. Do you want some kids?
Oh, like so he passed on those students to you. That's so nice. For math, right? For algebra? For math?
Oh yeah, algebra 2 and geometry.
Oh my god, geometry. I hate geometry. Like all those cosines. That's
I despise geometry with my whole heart.
There's like so many theoretical stuff, right? Like so many theories and everything.
It's so bad. I'm like, if there's no lesson plan, I can't teach it, which means it's a struggle during the summer because all the parents are like, oh, can you teach my kid this so that they're ahead? And I'm like, sure. Sure.
Yeah.
We'll see.
I know. Like you gotta prepare a lot more for those. I bet. Like those tutoring sessions.
Oh yeah.
Yeah.
It's so bad.
Oh my gosh.
And then you do this.
Yes.
Yeah.
Oh my god. X squared minus 3. Like I don't want to think about that.
What? It's so easy though.
Oh wait, hold on. Let me try. Let me see if my math skills are still there. So,
okay, you gotta use completing the square though.
So what does that mean? I don't know what that means.
Bruh. Okay. Wait. Where's my? Oh, there it is. There.
Oh wait, no, hold on. I don't know what I was doing. Let me redo this. Let me redo this. I just got something on my mind. Yes. Yes.
Mm-hmm.
And then x equals 6 and x equals -3.
Yeah.
Yes, I still got it, Kelly. I still got my rusty math skills.
You know how to factor.
Yes, yes. I don't know what I was doing before. I don't know why I was adding 18 on both sides.
I don't know why you were adding 18 on both sides either. Do you remember completing the square though?
By completing the square.
Yes, completing the square. Actually, this one will change it so that's -6. Because that's easier.
Give me a hint.
Do you remember what? Hold on, I'm blanking on the name now.
Pythagorean theorem.
No. That's linear stuff. Point form is linear stuff. Hold on. This is when I go to Google. Names quadratic forms.
Oh, quadratic formula.
No, that's not it. Oh, do you remember vertex form?
Oh, vertex form.
Yeah.
Vertex form. That's not y equals to mx plus b. That's something else, huh?
That's linear equation.
That's linear equation.
That's
oh my god.
Slope intercept form.
I'm embarrassing myself right now. I forgot. That sounds very familiar though.
It's okay, you're making up with OChem.
Yes.
I'm making up the lack of my OChem knowledge with that.
Yes.
You don't remember what it is, I'm guessing.
Vertex form. That's when you know the y-intercept and x-intercept, huh? No. Ignore me. I don't know. I forgot.
Not quite. It's when you have y equals a times x minus h squared plus k.
Oh my goodness. I don't remember.
And then h, I give h comma k is the vertex.
Yes, I remember learning about this, but I do not remember at all right now.
Okay.
I do remember learning this though.
I can show you if you want.
Okay, yes. Walk me through this problem.
Okay, so we have the square, right?
Mm-hmm.
It says complete the square. This is the square.
Yeah.
So what you want to do is you want to find the square within this formula.
Mm-hmm.
So if you have y equals x squared minus 6x minus 18, I'm going to first ignore this 18, so I'm only going to focus on this.
Mm-hmm.
And I'm going to have x squared minus 6x, and I want to complete it so that I have a perfect square.
9.
9.
Oh my god, yes!
And then, because it's 9, I added 9. And I have -18. I have to cancel out the plus 9. So what would I do?
-9 on the other side. Oh, +9 on the other side. +9 on the other side.
Plus 9 on the other side. But if I want to keep it to this side, what would I do?
-9 on the same side.
Yeah.
Oh,
-9.
okay.
So then I take this and I change it to this format. So I go x minus 3 squared. Simplify this. So -27.
Oh, that's how you do that. And then the vertex is -3, -27.
3, comma -27.
Oh yes. Because -3. That's +3. So +3, -27. Oh
and
my god.
If you have y equals 0, then you have x minus 3 squared minus 27. So then you move the 27 to the other side.
Wow.
Root it, and then you have x equals root 27 plus 3.
Oh, plus minus.
Plus
minus. Wait, why is it plus minus? Oh yeah, because -3 times -3 is 27. Oh my God. All this stuff is coming back to me now.
It's muscle memory.
Oh my gosh. Yes. Thank you, Kelly.
I know. You were enlightened with math.
Yes, I'm enlightened with math.
This was not necessary at all.
You know when the last time I did math was? Freshman year of UC Davis, when I was at UC Davis. So
17.
Yes, when I was 17.
17A?
21C.
Oh, 21C. Oh, so you did AP BC.
Yes, I did AP Calc AB, AP Calc BC, and I got 5s on both exams.
Nice.
And then I skipped straight to 21C my first quarter of UC Davis. And then after that, like, I did not touch math again. Like, it's been so many
You're like,
years,
nope,
I forgot.
no more math.
Yeah. Oh my gosh. Can you tutor AP Calc AB, AP Calc BC, Kelly?
I've tutored AB.
You tutored AB? Oh my God, that's good.
When I was taking BC. Because my friend was like, I'm struggling, help me.
Yeah.
So I helped her, and then I forgot everything.
Oh man.
Too sad.
It's too sad. I know. Do you like have any plans on tutoring for ATC UC Davis, like math or OChem? When you finish the class?
I applied for math.
Yeah.
But they didn't want me because they didn't finish the series.
Oh, the 17 or 21 series.
So I could have just gone to 21C right away. But my accounts, I went to advising because when I first signed up for classes during the summer before freshman year, I was gonna take chem, and then something weird happened in Schedule Builder, and they're like, "Oh, you can't take chem. It's like all full or whatever." I was like, "Oh, okay." So then I went to the advising center or like whatever, and they're like, "Oh, just take 16 or 17A," and I was like, "Okay." So then I just took 17A, and it was so easy, so
Oh
nice.
my God, yeah.
Didn't have to study for it at all.
That's great.
Then I was like, maybe I should do the 21C, and then I've just been putting it off until now and just haven't done it.
Oh wait, so you have to take 21C later, but next quarter maybe, or do you have it planned out?
I don't think I have to take 21C, but they were like, "Oh, your AP credits like make up for whatever."
Yeah.
But then I'm like, vet school requirements are weird, and they're like, "You need a year of math or whatnot." I'm like, so like, do you want me to take math?
Oh yeah, for
now?
vet school, right?
like
you need math for vet school.
They have weird requirements, like you need certain units of like chemistry or whatever. So like, if some schools say you need a certain number of units for OChem, but then the 8 series doesn't fulfill all of that because it's the quarter system, and they're doing semester units, and they're like, "Oh, like this many semester units," and you're like, "That's not enough with 8, so you have to take 118."
Oh yeah. Oh my God. Because you wanted to take the 8 series, but then you couldn't, so you switched to the 118 series.
I was a little stupid, and I was like, maybe I'll just take the 118 series to like open up my options, and I'm like, I don't even know what options I want. So.
Oh my gosh, yeah. Dang. That's crazy. It's crazy. I know.
Very crazy. I don't know why I'm doing this to myself.
It's okay. Like are you like you've been scoring around average, right? Or higher than average the beginning of the quarter, so
the first time I got a B. The second time I got an A. And then the third time I couldn't finish, so I got a C. And then the next one I got the exact same score, and I was like,
you were late, like 15 minutes late.
I was late.
You woke up late?
I woke up late. I woke up at 9:07.
Oh my God, so like you had to like rush and everything? Do you bike to school, or do you run, or do you take the bus? Or
I run so slow that I can't run anywhere.
Oh.
So I have to bike. And then
Mhm.
next year, or no, next quarter, I have to bring a car.
Oh, yeah. Do you have a license? Can you drive right now?
Thankfully, I can drive.
Yeah, that's good. That's good. That's good. So you don't have to learn like do that whole process and
Yeah.
everything. That's good.
I got an internship at this fine facility, and I was like, okay, I don't have much time in the mornings, but please take me anyways because I'm desperate for this.
Yeah.
And they were like, okay, do you have time like during this time? And it's right between my two classes, and I have to get there within 10 minutes of when my first class ends.
Oh my gosh.
So I have to drive.
Yeah, I know, I know. When did you land on your head when you got concussion?
Like what day?
Yeah. Oh, did you land like on your forehead? Did
Oh,
you
wait,
land
I have my helmet. I'll be right back.
Okay, okay. Oh, that's a different helmet than you showed me in the video.
If I'm going at the ground right now, I landed like this.
Oh my God. Did you pass out? Like, did you get knocked out?
I can't hear you.
Oh, okay, okay. Oh my God. Can you hear me? Hello?
Yeah.
Did you get like knocked out? Did you pass out? Oh, like did it hurt? Like was oh my God, it did. Like you landed like directly like that? Oh my God. Like right on impact, like your head first on the ground.
I felt like this.
Oh my God. Like that's the first contact that you had, like right there.
And then the rest of my face got it.
And then your whole body like tumbled over.
I guess.
Oh my God.
Like I don't know if you can see, but do you see like the little gap right here?
Yeah, I see that. I see that.
Yeah, it wasn't there before.
Oh shoot. So that must have some like big whiplash then on your neck, because like you landed like that and like your neck would have been like,
oh yeah, it
so
hurts.
messed up.
It's like oh
my
in
God.
the beginning I couldn't lift my head back.
Mm-hmm.
I still can't really tilt it back.
Tilt it back? You need a chiropractor.
You need to give me a discount.
A discount?
Yeah.
For free. It's on me. It's on me.
Oh really? Okay,
Yes,
I'll
yes,
go.
yes, yes. Okay, okay.
So, and then my face was really swollen because I landed like right on where my eyes were.
Yeah.
So then I
Oh.
had like a little imprint of my glasses right here.
Oh yeah, because like your glasses like hit your eyes as well.
They like pressed into my face.
Your face. Oh my God, Kelly.
And then this eye it had like a black eye or something under it. Like there was a big bruise down here.
Uh-huh. Oh my God.
Can you see it now? It's like almost gone.
Yeah, don't really see it. Maybe take the
Yeah.
glasses off, maybe? I don't know.
I'm gonna look bad if I take my glasses off.
Okay.
I look weird without my glasses. Yeah.
Mm-hmm.
The EMTs were hot though.
Yeah. Which ones were hot?
The EMTs were hot.
The EMTs were hot?
Yeah,
oh yeah,
they were pretty
they were
hot.
on site? Oh my God, that's good.
So I fell and I was like, well, I'm not getting up.
Yeah.
So then somebody came over and was like, you good? And I was like, I don't know. Am I good? And she was like, do you feel like you can get up? I'm like, I think I want to stay down for a bit longer.
Oh, was it the EMT that went up to you?
No, it was my instructor.
Oh wow, yeah.
And then she was like, okay, I'm gonna call the EMTs. I was like, that's a kind of smart idea.
Yeah. That's good. Oh my God. Dang.
My first ambulance ride.
First ambulance ride. Oh my gosh. What they do? Like they put ice or like rest a lot. Did they give you oxygen as well?
They put something under my nose that was like measuring
Oxygen.
my carbon dioxide. Something.
Yeah.
They put what's it called?
Oh, the blood pressure.
Yeah, that thing.
Yeah.
They're like, oh yeah, it's non-invasive, but it's totally invasive. Because every time I moved, it's like keep squeezing and squeezing. I'm like, Why is it doing this? And
I
they're
know, I know.
like,
It's a weird feeling having that whole like blood pressure going to go
oh yeah.
into you
And then
like
they put
that.
like a catheter in my arm, and I was like, it feels kind of weird. And they're like, just bend the arm. I'm like, fine.
You've been through it, Kelly. You've been through it.
Yeah, they put me in a neck brace and everything.
Oh yeah, that neck brace is like you just like had your big neck damage and head damage.
They're like, just in case, since you said your neck hurts. I'm like, yeah, that's a good
Yeah.
idea.
Yeah, that's good. How long ago was this again?
Good question. That's a very good question.
Mm-hmm.
It happened on the 22nd, so like 2 weeks ago.
2 weeks ago. Okay. Dang.
Fun times.
I know. And then like you're about to go back to writing the
Oh yeah, I rode on Saturday, and they were like, "Are you sure you're okay? You can do it. You sure?" And I'm like, "Yeah." They're like, "Don't push yourself." I'm like, "I won't." They're like,
Yeah.
"Okay." And they're like, you can try if you want. I was like, "Okay." And then after that, my back started hurting. I was like, "Oh, that was maybe not the best idea."
Oh my gosh, that's so good.
Everything just hurts after a while. I think I just got grandma-fied early.
You got grandma-fied?
Yeah, I got
Grandma-fied? What
grandma-fied.
the heck?
I became a grandma.
Oh my
Like,
gosh.
wait, there's like a reel on Instagram that's like, I achieved so many things at an early age, and it's like back pain, neck pain, arthritis, joint pain.
Oh my god. Grandma, and then you're like, how old are you? Like 21, 20 years old?
20.
20? Yeah. Oh
Achieving
no.
things that I should be achieving at 80 at 20.
Oh my gosh, Kelly.
Yeah.
You're living the life.
I know. Are you grandpa-fied?
I'm grandpa-fied. A little bit. I got some neck pain going on over here, but I've been getting right. I've been getting right with by my chiropractic like students, like not student, peers, and lab instructors. They've been adjusting me, so I've been feeling so much better. So.
Oh, so you get the free treatment.
Yes, I get the free treatments, Kelly.
Wow. Sometimes I wish I was a horse, because every like owner is like, oh yeah, acupuncture, chiropractor, body work, whatever. And I'm like,
yes.
I want all those things. Why can't I get all those things?
Oh my gosh. Soon, Kelly, soon.
I'm gonna go broke.
For free.
For free.
Yes. Okay, I gotta
when
uh-huh.
No, never mind.
Yeah,
you gotta
go. Yeah, I gotta go walk my dog and study for my exams. But like I'll give you your adjustments this Saturday when I come to Davis.
Wait, there's a little dilemma for that.
Oh, what happened?
So I thought that writing ended that past week, but then turns out it ends next week.
Next week? So you won't be able to make it this Saturday?
I don't know. Maybe not.
Shoot.
Wait, when is your thing? From 12:30 to what?
2:30 for one is in A.
2:30?
Yeah.
Okay, because I have writing from technically 1 to 2:15.
Oh, 1 to 15. Oh, sure. Oh, yeah, I get it.
I have to ask. It's gonna be a opportunity cost matter of whether I want a good grade or whether I want to have fun. It's rough.
Can you do it like is that the only day you could do it, or can you do it any other day?
It's the only day that I signed up for lessons.
Oh,
so
right,
lessons
right.
Days don't change unless I have like a medical excuse
Oh,
or whatnot.
yeah.
I don't know. Maybe they might be like, since you work here, but I don't know. I don't think they'll be too lenient.
Oh my gosh. That's a dilemma for sure. Kelly, that's a dilemma for sure.
It's a very bad dilemma. It's like, oh yeah, and then I said I would get there by 6 to clean poop. So
6 a.m.
Yeah.
Oh my gosh.
On both Saturday and Sunday. Yay. But
Dang.
money.
Yeah, I know, money. And experience too. Okay.
What kind of experience do you get from scooping poop?
We're like, I learned a lot from scooping poop. I
learned resilience.
Yeah.
I can push through. Sure.
Yes. I'll talk to you later, Kelly, and good luck. Good night. Yeah. See ya. Bye.
Bye.